This is the first part of a video series on the fundamental of heat load calculations. In this first part, we're going to be talking about building heat transfer, but first let's go overall what we're looking at. Okay, the reason we talk about heat load in an air conditioning troubleshooting course or in a heating troubleshooting course is that we need to take a look at, is the system correct for the building? Was it installed with the right sizing? Will it actually heat and cool the space properly? Or what do we need to do to get it to heat and cool the space properly? The fundamentals of this is you have to do a heat load calculation. And you have to understand the numbers if you're using an electronic tool to do that heat load calculation. So let's start by taking a look at the building heat transfer. Okay, we have to remember that the purpose of a heating system is to bring the controlled environment to a set point and then to replace the heat lost. We also have to talk about, the same thing can be said for a cooling system. The difference is we're going to either reject heat or replace heat. So what causes heat loss? It's basically a temperature difference, okay? If we have a cold outside day and a warm inside environment, we have a temperature difference. That is the primary cause of heat loss. So let's take a look at what heat loss is, what causes heat loss, how heat loss is measured, and what affects the rates of heat loss. Heat loss can be set into two different categories: transmission losses and infiltration losses. Transmission loss is heat transfer through confining walls, glass, ceilings, floor, or other surfaces, and that's according to ASHRAE. Okay, so what do we mean here? Heat that moves through the solid objects. Okay, so if I put my hand on the inside of a window and it's cold outside, I feel the window being cold. There's heat transferring out of that window. Cold doesn't transfer in, heat transfers out. Infiltration loss is a little bit different. Infiltration losses is basically energy required to warm outdoor air leaking in through cracks, crevices around doors and windows, or through open doors and windows and through other porous building materials. Okay, so infiltration loss has to do with like breezes blowing through cracks and crevices. Anything that's a porous material. You can feel infiltration losses most often because it will feel like air moving. Okay, so let's start with transmission losses and narrow that down a little bit further. Okay, we have to look at yourself as a heat source. It's called the human heat source. Why do you wear a coat, scarf, gloves, and long pants in the winter and shorts and sandals in the summer? It's real easy. The human body creates heat. Okay, how much heat and where does it go is the problem. Okay, so how much heat your body creates depends on the activity. An office worker gives off about 500 BTUs per hour. And that's a sort of important number because that's a person sitting still doing a task at a desk. The human body at rest produces about the same amount of heat as a 100-watt light bulb. So the heat leaves your body and always goes to a cooler place than your body. This isn't always desirable, and it leaves at a rate that's relative to the temperature difference between your body and the surrounding environment. So let's say your body is at its normal temperature, about 97 degrees, 96.8, 97, close enough. Okay, and the outdoor surrounding temperature is at 76 degrees. That's a 20-degree temperature difference. Okay, your body will have a certain rate of heat loss. If I lower the temperature of the surrounding area, okay, to let's say 30 degrees, all of a sudden the heat that is leaving your body is going to leave at a faster rate because of that temperature difference. Okay, so it leaves at a rate that's relative to the temperature difference between your body and the surrounding environment. So let's say you're standing outside in the winter in the north. You have no protection. Okay, any heat your body generates is transferred immediately to the surrounding cold environment, and you feel really cold. Okay, the space around your body is 10 degrees. You're losing 10 degrees. It's negative 10 degrees outside. You're immediately losing that heat. And you're not going to last long because you're going to be really, really cold. Okay? Let's build up a little box around yourself and provide some insulation from the outside. The heat from your body slowly warms the air around your space. Okay, this is your little box. Okay, the heat from your body is slowly warming the air in the space. So I still have negative 10 degrees outside, but 0 degrees inside. Okay, so we're slowly warming up. Except, since there's still an imbalance, okay, and you don't have insulation, the heat leaves faster than your body's ability to generate it. So you're still going to get cold because there's no insulation around this cardboard box. It's going to always try to migrate and cause a perfect balance between the environments. You add a heat source to your space. The temperature starts to go up. Okay, see, I've added a little fire. The temperature's going up. But then here comes nature again. And this time, she just steals it at a faster rate. Again, natural tendency for heat is to always create a balance between all temperatures. A bigger fire can eventually overcome the rate at which nature can steal it. But it costs money to have that bigger fire. So the cost of the bigger fire will start to hit the pocketbook. What can we do about it? Okay, this comes down to outdated construction methods were based on cheap fuel. One overpowered heat loss with a larger furnace, resulting in larger quantities of fuel being used. And while fuel and energy costs are going up, this method anymore isn't the smartest design. We're left with many legacy buildings which leak like sieves and have energy-devouring, oversized heat sources. Okay, same side on the cooling. Okay, just because we're talking heating on this slide doesn't mean air conditioning is the same. So along comes an installer doing the best job they can possibly do. They take a look at the size of the building. They say, well, wait a sec. This furnace is way oversized for this size of the building. Okay, and they put in a furnace based on the square footage of the building because everything's more efficient now. Okay, so we put in a lower BTU output furnace or a lower BTU output air conditioner, and all of a sudden, it doesn't do its job. Why? Because the building is 30 years old and it doesn't have the same energy efficiencies as the buildings today have. Okay, so using appropriate combination of insulating materials and heat sources, we can finally achieve the desired temperature. The point is maximizing R value of the building shell, that's the insulation value, is to slow down nature's tendency to equalize imbalances. If you can retain the heat, then you can reach your set points or levels of comfort without having an unnecessarily large heat source. The more insulation, the slower the heat loss, and the smaller the heat source is required at design temperature. When in equals out, the temperature remains constant, and that is called the balance point. Let's look at a couple examples. Again, nature hates temperature imbalances. So for the first example, set a hot cup of coffee on a desk in a comfortable room. Come back in a few hours. Is it still as hot as you left? Why not? Where did the hot go? Well, I'm going to tell you it's not going to be as hot as when you left it. And the hot migrated to the cooler air around it. Look at another natural imbalance. Set a glass of water with lots of ice on a desk in a comfortable room. Come back a few hours later. Is it still as cold as you left it? Why not? What happened to that cold? Real easy. It's not going to be as cold as you left it. The reason is because there's an imbalance between the ice water temperature and the temperature of the room surrounding it. What happened to that cold? Okay, well, it's not what happened to the cold, it's what happened to the heat of the space surrounding it. And we're going to talk more about that next. You have 4 things you have to remember. Hot always goes to cold. Cold never goes to hot unless it's done mechanically. Okay, so heat always tends to move to the colder air. Hot goes to cold at a rate relative to the temperature difference. Okay, so if my hot and cold is both at 70 degrees, I'm at a balance point. Nothing's going to change. If I drop the outside temperature to 35 degrees, the hot, which is 70 degrees, is going to attempt to take the cold and bring it up to a balance of 70 degrees. This is what's happening on a cold day, outside temperatures. If I have a really hot cold, you see how the ball went to a different speed, okay? If I'm here, we're going at a slightly slower speed. All of a sudden, it's a faster speed because the temperature difference is at a greater rate. So we've talked about hot goes to cold. Hot goes to cold at a rate relative to the temperature difference. And radiant heat goes from an infinite number of directions from the source. So we haven't talked about the type of heat yet. But let's talk about radiant heat. Okay, heat is lazy. It's going to follow the line of least resistance. So think about a sun or the sun, okay? Rays leave from all directions of the sun. Okay, it's going to follow the line of least resistance, which is a straight line. Okay, so if heat is trying to leave through insulation, it can't necessarily leave through insulation. That's an insulated wall up here. Okay, so heat is going to bounce off the heat source and bounce off the wall. Okay, as long as the insulation is thick enough, heat will stay on this side of the insulation from the heat source. Insulation has a lot of resistance. Some will not penetrate, some will go through. Some is reflected. Radiant heat goes an infinite number of directions from the source. Okay? Not just up. Okay, don't always believe the idea of heat just rises. Heat is lazy. It's going to follow the line of least resistance. Okay, so those are 4 important things. Hot goes to cold. Hot goes to cold at a rate relative to the temperature difference. And radiant heat goes an infinite number of directions from the source. Heat is lazy. It's going to follow the line of least resistance. If the least resistance is bouncing back into the space or bouncing back out of the space, that's where it's going to go. That's why we consider insulation is resistance to heat transfer.